On the 90th episode of the How Do You Know program as we launch our 4th season. So excited. Friends, if you haven't done so yet, I strongly encourage you to check out my book, Star Mentor, on Amazon. If you are new to astronomy or you know someone who's starting in the hobby, the best recommendation I can give you. I always tell people I'm not here to sell books. I'm here to set hearts afire for astronomy. I want you passionate, involved, and enjoying this hobby for years to come, and Star Mentor is an excellent way to get started down that path. Now, let's talk about what's in the news today. NASA is planning on sending cryobots to explore the icy moons of Jupiter and Saturn. You may have heard that icy moons such as Titan, Enceladus, and Europa may have subsurface oceans. We've seen plumes of water with organic materials, and this would be an excellent and interesting place to look for life. How do you do that when the life may be swimming in an ocean that's miles down under the ice in a subsurface ocean? Well, it turns out that you don't need a whole lot of power. A 10 to 15 kilowatt radioisotope generator, similar to what we send to power the Mars rovers, could melt through miles of ice. But that's not the only challenge. There are 2 other primary challenges scientists are working on. One, how do you maintain communication with the mothership on the surface? Are you going to send a wire? Might the ice shift and break that? Can we develop wireless communication that'll work through that much ice? The other thing, of course, if you're going miles down, is pressure. We all know what has happened to submersibles that have gone deep into the ocean looking to explore Titanic and other shipwrecks. If these things aren't well built, the pressure will crush them in an implosion. So that's a couple of challenges that we need to work on. But we think this is a great place to go, and it's a tremendous scientific challenge. So we'll look for more from NASA on this as things go on. The next item we have is that these were popularized in Star Trek as nanites, nanoscale machines. Stargate, yes, Stargate, and Arthur C. Clarke, 2010, the year we made contact. SG-1. So, yes, these are
to sleep at night.
Actually von Neumann universal machines or universal constructors. These are machines that can use local resources and make more copies of themselves. In fact, all biological organisms are von Neumann machines. A single-celled organism like a bacterium uses resource, makes more copies of itself, and we're like, well, that's bacteria. How hard can that be? Reverse engineering this is quite the challenge. But in fact, we're looking at some articles in New Scientist, if you want to check out the links at the show notes. These nanites are made of just 4 strands of DNA. Why work hard to come up with a new method when nature has come up with one that's worked for billions of years? These are 1,000 times smaller than a human hair, and DNA like this could be used to manufacture drugs, enzymes, more copies of themselves inside the body, and they can be controlled and programmed, if you will, I don't know if that's too strong a word, by the use of external temperature and UV light. So scientists, by using pulses of heat or UV light, can actually control these things to express their genes and make copies of things. Wow. The other thing is the exact strands of DNA. that make these up are unique and not found in nature. So they shouldn't run amok like a sci-fi movie, but then again, we'll keep a close eye on that. The third news story we have today is wrong. When I prepped this show a few weeks ago, and we got postponed because a couple weeks in a row we've had ice storms and terrible weather here in Arkansas that, frankly, we are not prepared for.
Yeah, it was almost over a month ago.
It was about a month ago we were supposed to start. And at that time I wrote, OSIRIS-REx is still stuck. But that's not true anymore. NASA has opened OSIRIS-REx, and they have found lots of material. You may remember that the goal of the project was to bring back 60 grams of material. They found more than 70 grams of material just collected on the outside of the OSIRIS-REx probe. And now they've opened it up. The inside was full of just chock-a-block full of lots of black and powdery substance, glints of metal, all sorts of things. And interestingly, most of this sample will not be touched by scientists anytime soon. You realize that what we do with samples of this sort is we archive them. We take a little bit, we distribute it out to scientists and qualified labs around the world for their research, but most of it is archived. Why? Our assumption is that science and technology will continue to improve. Do you know there's new samples of Apollo moon rocks being sent out today that have never been looked at before? They're being pulled out of the archives. Scientists say, we have these new analytical techniques and we'd like to go back and look at the Apollo rock. NASA evaluates, and if they approve, they say, sure, here's your sample. So we should be learning things from the OSIRIS-REx probe about asteroid Bennu and our solar system for many decades to come, because we had an absolute bonanza of material in this TAG SAM sampler. The challenge was when the bolts were stuck, NASA had to design new tools. Not that screwdrivers don't exist or even impact wrenches, but they needed something that would fit inside their sealed sample laboratory, this very tightly controlled environment, dry nitrogen gas flowing over the sample so that nothing happens to it, because we've got it here on Earth. And they use special non-magnetic stainless steel of great specificity, and they got these tools. I hate to think what a crescent wrench from NASA has to cost, frankly, but they were able to get inside this sampler, and that's very exciting. We'll look for more news on asteroid Bennu and OSIRIS-REx. So let's go ahead to today's topic, exploring the mysteries of Hawking stars. When I posted this topic on my Facebook page, I immediately got questions back from friends. What are Hawking stars? I've never heard of them. So let's go ahead and back this up a bit. Every story in astronomy has a backstory. So think about this question, friends. What would you do if you wanted to hide a black hole? Why do we ask this question? Well, first, black holes are notorious. They devour anything they touch, right? How would you move one? If you want to move a pen or a mug, it's simple. You grab a hold and you lift it and move, but you can't do that with a black hole. No touchy. That would be a bad day. Well, and if you could move them, could you find them again? It actually turns out that black holes do give off a fair amount of radiation when they're feeding. When they're consuming material, it's falling down the maw of the black hole. That material gets heated up. It does give off X-rays, which are a notable signature. You may remember the very first black hole, Cygnus X1, was detected because it was a strong X-ray source. The other thing black holes give off is jets. They give off jets from their polar regions when they're ingesting material, and this makes it possible to find them. So if you're going to hide a black hole, what would you do? It's an interesting question. And why would we worry? Who would hide a black hole? Well, it turns out there's a kind of black hole you may not have heard of. These are referred to as primordial black holes, and they're strong candidates for that mysterious stuff we call dark matter. Now, primordial black holes, PBHs by some people's moniker, these would have been created at the very beginning of the universe, shortly after the Big Bang, when the universe was so hot and dense that small microscopic black holes were being created. They were collapsing directly into atom and molecule-sized black holes, maybe something slightly larger, but not very much. And these were being created spontaneously, we think. However, we have no evidence that they're actually there. All the theories say they should be there, but there's less data showing existence of primordial black holes than there is evidence showing the existence of dark matter. Well, if primordial black holes are dark matter, how come we haven't ever detected any? There should have been a great many of them. So even though the universe has expanded tremendously since the Big Bang, it still should be possible to find one, but nobody ever has. And that brings us to the idea of what makes a Hawking star. Well, we step back to our earlier idea, how do you move a black hole? And the answer is with gravity. Think about this as a thought experiment. If you were in a solar system far from here, perhaps in a galaxy far, far away, if you're in a solar system with a star and nothing else, and you're there in your spacesuit floating, there's the sun. If you took a rock and just tossed it away from you, where would that rock end up? Well, since you're in the gravity well of that star, basically everything in that solar system would fall down eventually into that sun. There's nowhere else for it to go, and you, as an astronaut, couldn't pitch a fastball fast enough to get that rock to go out of the sun's gravitational well. We think primordial black holes may have come to the same fate. So think about this. Black holes being created before the first stars, before the first galaxies. So the early universe is full of these little monsters, and now stars start to be created. The nice thing about stars, we've talked about this before on the How Do You Know program, stars form when you have molecular clouds that are dense enough that they collapse under their own gravity. So all the particles of dust and gas flow in to a central gravitational well, a central point where the gravity collects these materials, they compress, the star ignites. Well, quite possible if there's primordial black holes in the area, they too would be captured by that star's gravitational field. Now, if we're capturing a primordial black hole, and it did indeed fall into a star, my first question when I heard this idea, goodness, why didn't the star immediately get devoured? Black holes devour everything. Well, yes and no. If you think about a black hole, if you have a black hole that's a stellar mass black hole, this thing's going to be a reasonable size, and we know that supermassive black holes may be as large as our solar system. But the fact is, you can think of a black hole as a hole in space-time. Things that fall down the hole don't come back again, and the bottomless pit of gravitation that is a black hole. However, the black hole has a surface area. We can measure it in square centimeters, square kilometers, doesn't matter. But the black hole cannot devour anything larger than its own surface area. In other words, you have to be able to fit whatever you want to consume down the throat of the black hole. So consider a primordial black hole the size of our moon. Okay, if you had a black hole the size of our moon, this would be many solar masses, and you went and dropped that into a star. And yes, this has been done on science fiction shows. Go back and look at some of the Star Trek movies and you'll see, oh, red matter. And they hint around that this is supposed to be some kind of black hole stuff. And they drop it into stars and into planets and destroy them. Well, turns out that would take a really long time. So if you had a black hole the size of our moon that gives it quite a lot of surface area, this still would take hundreds of millions of years to consume all the material in a standard yellow dwarf star like our sun. Hundreds of millions of years. So even a Jupiter-sized black hole, if you think, oh, we've got primordial black holes, these should be very, very small, atom size, molecule size. Even if you had a Jupiter mass, took Jupiter, compacted it down into a black hole, you'd still have something less than 3 meters in diameter. If something the size of the moon, a black hole the size of the moon, would take hundreds of millions of years to devour a yellow dwarf star, something the mass of Jupiter, a Jupiter mass black hole, that would take billions of years to devour a star. And it turns out the story gets even more interesting than that. The stellar department at the Max Planck Institute for Astrophysics in Germany is run by a professor named Selma de Mink. And Professor de Mink and her team have been investigating these ideas. Quite fascinating. And they basically said, okay, if primordial black holes did indeed form using our current model of the Big Bang, they would be very numerous and quite densely spaced between the stars. The thing is, we don't see any evidence for this. If we had even a moderate density of primordial black holes between stars, then we should see evidence for plenty of them in our galaxy and in our local group of galaxies. We should see plenty of evidence. We should see radiation. We should see polar jets. We should see evidence of microlensing, all kinds of stuff. We don't see any of that. Now, if you're looking for something and you can't find evidence that it actually exists, you've got a couple of possibilities. One, they're much rarer than you thought. We have no mathematical reason to suppose this. Two, they're somehow hidden. Okay, and they're somehow hidden. And where would they be hiding? And if we look at that, Professor de Mink speculates that these plentiful primordial black holes would indeed have been swept up in these condensing molecular clouds in the early universe. And they would have been quite naturally, just like the gas and the dust and other materials in those early molecular clouds, these primordial black holes would simply have been incorporated into the stars that were forming there. If you're out this winter braving the cold and looking at the Orion Nebula, one of my favorites, and you go ahead and go, ooh, I want to look at the star forming region. When you're looking at that dense nebula and you see, oh, there's the group of stars in at the center, the parallelogram, and you think about, gee, there could be primordial black holes in that molecular cloud being condensed and swept up with all the other gas and dust and material, and those black holes could be incorporated into stars, just like, things get incorporated into the body of a growing organism. Oh, hey, mom's consuming, calcium and carbohydrates and protein, and the infant in the womb is incorporating these things in the stellar womb that is the Orion Nebula. These black holes, these primordial stars could be feeding on primordial black holes and incorporating them as they grow. Turns out that if you're talking an atom-sized primordial black hole, and that's where the theory runs to, if you're talking about an atom-sized black hole, these things would take more than the current age of the universe to absorb and consume a standard dwarf star. So we look at this and we say, well, if these black holes could have been incorporated into these early stars as they formed, are there stars without them? And if there's with and without, meet and meet out, as my butcher used to say, then in fact, if you're talking about these stars with and without black holes, how would we detect and tell the difference? How do we tell the Hawking star from the Poser that's just a regular star with no black holes in the center? Well, if you're going to detect one species of star from another, you have to have some idea about how these stars function. Let's take a look at this. If you take a look at Hawking stars, a Hawking star would look just like any other ordinary star. The color, the temperature, the surface features would all be the same. These would still follow the Vogt-Russell theorem, which says that the mass and composition of a star determines everything about it: size, fusion type, luminosity, color, lifetime expectancy, method that they will die, and the remnant after they die. The Vogt-Russell theory says everything about a star is determined by the materials used to make it. Turns out adding a black hole isn't going to change any of those common things. Well, the deal is, and again, tip of the hat to science fiction folks here, we've hypothesized for many, many decades that in fact, if you could have a tamed black hole, something that you could have and isolate and utilize without destroying yourself, well, you could use a black hole as a power source. If you had material to feed into it, this raw material is going to produce a lot of energy in X-ray and other radiation, which could then be harvested. If you think about a black hole inside of a Dyson sphere, right? A constructed technological sphere that surrounds a stellar object, well, if you were feeding material in, you could in fact extract rotational momentum, heat, and other types of radiation, which could be turned into electricity and other sources of power, and you could use a black hole as a power source. Well, this black hole, this primordial black hole buried at the core of a star, would in fact function as a second power source. Instead of a star powered simply by fusion energy, fusing hydrogen into helium, this star would have a second power source of material, hydrogen, helium, etc., falling down the throat of the black hole, and the black hole would extract energy and release it into the star. And so this would help power the star. So we look at this and we look at how regular stars work. You've probably seen this in a science class somewhere. The star has a core, our sun has a core, and this is where fusion occurs. And the fusion powers the star and releases radiation, and we have what we call above the core, we have a radiative zone. This is where energy is released as photons of different frequencies, anywhere from infrared up through gamma. And this material radiates out. It's not a fast process. The calculations say that it takes a photon hundreds of thousands of years to make its way from the core of a dwarf star out to the surface where it flies out. Why? Because the photon is released somewhere in the core. It owns a very dense environment. It only travels a short distance. It hits another particle, it's absorbed, and then it's re-radiated. The catch is, it can be re-radiated in any direction at all. It could be re-radiated back into the star or sideways. But eventually, and this is the miracle of statistics, we can say, okay, how dense is it, and how far apart are the 2 points between the particles, and you can calculate this. It's known as the drunkard's walk problem, if you want to look up the mathematics of it. And these stars, the normal star has a radiation zone, and then outside of that, there's a conductive zone. The Earth has similar type structure. It has a conduction zone inside the mantle where the rock circulates and new crust is brought to the surface. Old material is drawn back in and recycled. And this convective zone happens because as this plasma gets out towards the outer regions of the star, it releases energy, cools off, and then sinks back in. If you boil some pasta on the stove for dinner tonight, you can see this exact type of convection. You'll see hot water and pasta and bubbles coming up from the center of your pan where the flame is. They reach the top, they move outward, they cool off, and they sink back again. You can look into a boiling pot of macaroni, and you can clearly see these convective cells. And works the same way in the Earth, it works the same way on the sun. But in a Hawking star with 2 power sources, it's different from a normal star. Instead of having a radiative zone and a convective zone, a Hawking star, the core becomes convective. The core now cycles up and around, just like your boiling pot of macaroni, just like plumes of magma in the Earth's interior, just like plumes of plasma in the outer layers of a normal star. So the effect starts small, to be sure, but it's going to continue to increase as the eons pass and the black hole devours more matter and becomes larger. And as it becomes larger, it's going to be consuming material at an accelerating rate and powering the star at an accelerating rate. To me, this is really fascinating because we normally think of the fusion power of a star as something that runs at a pretty steady rate for millions of years, and then the fuel dies out and suddenly the star collapses, and what happens after that depends on a lot of factors. But we know we get this ramp up, fusion ignition, and then everything is steady state for quite some time, and then there's a collapse when fuel runs out. Hawking stars would be different. They would have a second power source in their core, which gets steadily more powerful over time. There's none of this ramp up and then steady state for a long time. The black hole continues to grow, and its contribution to the power of the star continues to grow in a more linear way. So, okay, 2 power sources. We've changed the dynamics of the interior of the star, but we've already said the outside, to somebody, say, on the surface of the Earth looking at the sun, well, how do we tell? We've already told you. The color is the same. The radiation spectrum is the same. The lifetime, as far as we can measure as human beings, is the same. So how do we detect that? Turns out that this second power source does something else. It effectively causes the star to sing. What do we mean by that? Well, again, let's take a simpler analogy. Let's consider a bell, like a church bell or a gong, doesn't matter. And you strike this bell and we know that, oh, it reverberates. We can hear the bell because the vibrating of the metal sets up pressure waves in the air, and we hear a musical tone. We go, the church clock is striking 6, and we can hear the bong, bong, bong of the chime as the clock strikes. Well, stars are not much different. What makes something oscillate? It simply has to be able to support either a translational wave or a compressional wave. Stars, being made of plasma, do compressional waves just like air does compression waves. I'm talking right now. Pressure waves come out from my mouth. They travel out. They're being picked up by the microphone and transmitted to you. But it's this oscillations in pressure. And of course, these oscillations have frequency, pitch, all those other things that we know about. Well, it turns out you can, in fact, look and see a star singing, vibrating. This is referred to as astroseismology. We do the very same thing with the Earth and now with Mars, where we use earthquake energy, seismic waves. These are compressional waves, just like effectively sound waves, and they travel through stone and they travel through, they get deflected by the liquid, they get reflected by the core, and there's a whole field of science there, friends. If you want to look at seismology and how earthquakes probe the core of a planet, that's a fascinating bit of science to delve into. Turns out we can now look at stars and we can measure starquakes, and we can see from big events happening like coronal mass ejections and prominences and solar flares. These are tremendous blasts of energy being released from the surface of a sun or a star, and this energy also causes the star to vibrate, and we can watch these waves and we can actually see them if we have high enough resolution solar photography. So we think we should be able to look at stars, and if we can see their vibrational patterns, if we can measure them, then we should be able to isolate the difference between a normal star and a Hawking star. Now, that would be for standard stars on their main sequence journey. So we can look at for stars like our sun, and of course the challenge is the sun's only 8 light minutes away, whereas other stars are many light years away. So obviously we need to have very sensitive telescopes and detectors that can see this vibration and measure it precisely enough to be useful from Earth in order to see if we can actually detect this. This is a very new field, hasn't been around for very many years. Literally 21st century astrophysics. So that's one possible method. We're going to look at the vibration patterns. Obviously, we're going to need a large database. So once we get a successful astroseismology detection, and I'm sure just like planet hunting, the range and power and sophistication of the method will improve over time, but we want to be able to reach out to stars. We could measure the solar acoustics within, say, 500 million light years or even 500 light years. That would give us a great database of stars, and we could start comparing them. Do we have clearly 2 sets of data? One that conforms to a Hawking star theorem, and one that says, no, I don't have a black hole in the center. But obviously, trying to detect these things from a sample of 1 becomes extraordinarily difficult. There is another possible detection method. One of the things we can do is we can look at, gee, what happens to a Hawking star near the end of its lifetime? Well, if you think about what kind of stars do we have that are close to the end of their lifetimes, and the answer is, of course, red giants come to mind immediately. Many of you who are fans of the show probably were out and looking at the red giant Betelgeuse a couple of winters ago, when we were looking at Betelgeuse dimming suddenly by about 60%. And everyone got very excited. Maybe it's going to blow. Maybe it's going to blow. I wanted to see that supernova in my lifetime. That would be so exciting. It didn't happen. So we figured out why Betelgeuse was dimming. It wasn't getting ready to go supernova. But in fact, think about one of these stars with a black hole at its core. This is a star that would have had a black hole at its core for hundreds of millions, maybe even billions of years. Well, if you've had this cosmic ulcer, if you're a star and you've had this cosmic ulcer, this black hole sitting at your core and literally devouring you from the inside out, which kind of sounds like some kind of creepy alien science fiction movie. But if you've got this monster in your core devouring you from the inside out, what does it look like after several billion years of stellar evolution? Remember, yellow dwarfs that make red giants, they're somewhere in the range of 10 billion years old. Well, if you've had a black hole at your core devouring material for, say, 10 billion years, isn't that going to change things? And yes, in fact, we think that after a time, these primordial black holes, because they're consuming more and more of the core, they're going to start really changing what the star looks like, its appearance, and lots of other things toward the end of its lifetime. Keep in mind, a Hawking star with a black hole at its core, to kill that star, doesn't have to eat the whole star. It just has to devour the core. Once the black hole at the center devours the core, which is much less than the mass of the entire star, once it devours the core, that star no longer has a fusion power source. Now it's a large ball of plasma being powered exclusively by a black hole. So even when the star died from its black hole ulcer, it wouldn't immediately like slurp, wink out and go away. But the fusion would stop, and scientist Dr. Demink and her team in Germany suspect that the central black hole, after many billions of years, these would start to make the star cooler than standard stellar models say it should be. The Russell-Vogt theorem and the theory of stellar evolution in general is quite evolved. That science has been around for about 100 years, and we've learned an awful lot about how stars grow, evolve, and die, and what happens as they die, and what kind of a remnant is left over. But we look at these stars at the end of their lifetime, we have very accurate models for how hot and how energetic these ancient red giants should be, what the energy spectrum should be coming out of them, and we have a lot of data from models to check against actual stars. Well, it turns out that from stellar surveys, we know more than 500 red giants, which are, in fact, cooler than they should be by standard models. These give us an excellent indication of where we should look to start practicing our stellar acoustics and looking for these vibration signals that indicate a black hole power source at the center. Now, if we have a black hole at the center of a star and the star is aging, the central black hole is consuming more material, then what happens when the black hole dies, when that star dies? And there are competing theories on this. One is that once the core has been devoured, the star will essentially start to fade, and essentially what you're going to have is an energetic black hole that is consuming material from the cloud of gas and plasma that surrounds it. Do we know what an actively feeding black hole looks like? In fact, we do. And we have a couple models for this. In the early universe, these are referred to as active galactic nuclei, or the old term for them, quasars. What are we looking at with a quasar? A supermassive black hole at the center of a galaxy, feeding literally entire stellar masses at a time. And we know that quasars are quasi-stellar objects. These are very bright, compact objects, and they're giving off more energy than a normal galaxy does. Where's all this energy come from? That infalling matter swirls around the black hole. It becomes an accretion disk, and this material, as it swirls, as you can imagine, the stuff in the center spins faster than the stuff on the outside. You may have seen this sort of thing at a carnival or a county fair. There's this parabolic funnel, and you roll marbles down or coins down. I've often seen them as fundraisers where you roll a coin, and the coin rolls around very slowly at first, but as it moves down the throat of that funnel, it spins faster and faster and faster, finally too fast to watch. You're just hearing it hum, and then clunk, your quarter disappears and you've donated to the Red Cross or Goodwill or whoever. Well, this idea of the material spinning faster as it falls in, if we think about this, then the different zones, different orbital regions at different radii, different distances out from the black hole, are spinning at different speeds. If things are spinning at different speeds, they are effectively rubbing against one another. That generates heat, and so much heat that these disks of material get hot enough to emit in X-rays and even gamma rays. So these active galactic nuclei, supermassive black holes with monstrously large, light years wide accretion disks, and this material is swirling down, getting heated to unimaginable temperatures, and in fact radiating off tremendous amounts of energy, which is what makes a quasar. Now, is it possible that we're going to have a red giant, which has become kind of a mini active nuclei? Wouldn't be galactic size, certainly. A mini stellar nucleus, a black hole nucleus. The balance of the star's material would simply get shrunk and compressed into this lovely accretion disk, and the accretion disk would heat up and radiate heat in all parts of the spectrum. But there's another possibility. There is another possibility, and that has to do with something we call disappearing stars. Now, the idea of a disappearing star, when I first saw this in one of my searches, I'm like, oh, come on, disappearing stars? It sounds like some clickbait, phony baloney story. In fact, it's not. The earliest case we know of was in 1952. And they were doing a stellar survey at Palomar, and they were looking for objects inside our solar system that were moving. So they're essentially taking Starfield, take a picture, wait a few hours, take another picture, and then they use the modern version of a blink comparator, Clyde Tombaugh's technology, to compare the two images and see, oh, is something joggling back and forth? Well, gee, that's something that's moving. And so, ooh, it could be an asteroid, it could be a comet, could be some other material. And so they were really looking for things that were going across their field. They found something they didn't expect. First star field, plenty of stars. Second image, plenty of stars, -3. 3 of the stars in that star field disappeared over a period of just a few hours. Now, we were not in 1952 taking a video so we could go frame by frame and say, there they are, there they aren't. We simply had the 2 photographs, and what happened in that time gap was something of a mystery. Now, there are special kinds of, I suppose you could call them supernova. I don't know if the name is actually apt, but this is called a direct transition, where you have a star, and at the end of its lifetime, it runs out of fusion fuel, and instead of having a nova and then the explosion compresses the core material to form a black hole, scientists speculate if you had just the right conditions, when the star died, everything could collapse directly into black hole state without a nova explosion. Think about that for a minute. We've all come to grips with the idea that stars die, and then you either get a white dwarf, a neutron star, or a black hole, but this is accompanied by a titanic explosion. Releasing in a supernova can release more energy than the entire galaxy does. And tremendously powerful energy sources. Basically, within 50 light years of a supernova, pretty much everything dies. It's a bad day if something in your local neighborhood goes supernova. But we suspect, theorists suspect, that you could have it just right and just compress directly to black hole state without a supernova explosion. This has been proposed for a possibility. They could have had this 1952 disappearing star could have been, in fact, the first direct evidence of a direct transition to black hole without a nova. Now, when we look at this and we get this idea, the star could, in fact, be consumed from the inside out, and instead of a direct collapse, what if that was, in fact, the end state of a Hawking star? Once the core is devoured, there's no more fusion power. The main engine producing light and heat wouldn't be there anymore. There would be no mega bright flash. There would be no bright light with a well-predicted decay. We understand supernovas quite well. We can watch them, we can see the luminous intensity peak and then die away over time. And from our mathematical models, we can tell you what kind of supernova it was. We can tell you how big the star was when it died. But we really aren't sure what a direct transition to end state for a Hawking star would look like. We're quite sure, relatively sure, the models say, I have to qualify all of these statements when we're talking about the bleeding edge of astrophysics. We think that, in fact, these direct transition to black hole, the black hole at the center consumes the core, Consider this. What happens during a regular supernova? The fusion power dies, but all the mass is still there. If you have helium fusion has ended, right? You've run all the way up from hydrogen fusing products to iron, all that mass is still there. And when fusion power dies, the star's outer layers are no longer supported against gravity. And in fact, with they're no longer supported against gravity, they infall at almost the speed of light. They hit the core and they compress it, and at a certain point it bounces. Effectively, that's what creates the supernova. And the explosion, which does not originate at the core, the explosion originates in a spherical region around the core. Explosions go bang in all directions. Most of it goes outward. That's the bright supernova we see. Some of it goes inward and compresses that remaining material into a white dwarf neutron star black hole. What happens if you already have a black hole in the middle? What happens if all the core material, the majority of the star's mass, has already been incorporated into a black hole? Now, the amount of material infalling isn't as great. Matter of fact, it's different perhaps by an order of magnitude than an ordinary red giant core. And all this material isn't falling into a hard iron core. It's actually falling onto a black hole. And so we suspect that, in fact, this black hole material could, in fact, fall in, and these stars may transition directly to a black hole. And, in fact, disappear. They could go from luminous to non-luminous in a very short period of time. Now, this would explain the 3 disappearing stars that we found in the Palomar survey in 1952. And in fact, we found some more than 100 other examples of, oh, here's a star field survey, somebody else, here's another one, and you're looking at, oh, there's a star missing. Now, for a human being to look at a star field and go, gee, that star right there in the corner, see that one, that's gone, that would be a Herculean task. But computers can do this very quickly, and computers can go back and examine all these previous plates. There's a lot of data that's been collected from photographic astronomy over more than a century, so there's a lot of things to look at. But in fact, we think that these Hawking stars, the end state, could also explain our disappearing stars, and we think, at least Professor Demink thinks, that in fact, these could explain these direct transition events, and they could be where our missing dark matter is. We've all heard of the idea of dark matter halos. Could these be primordial black holes in a halo around a galaxy? Quite possibly. So, and there may be more than one kind of dark matter. So we are indeed pursuing this with great excitement. Mr. Producer, did we get any interesting questions today from our social media?
Well, Glenda Taylor,
Yes.
she says, awesome. Julian said, iRobot.
iRobot.
Yeah. John Ray says, hello, Dr. Barth. Good to have you back on. Happy New Year from Cornish Flat, New Hampshire.
Indeed, Cornish Flats, the epicenter of our fan system here. John, glad to have you back watching the program.
And then we have Misadventures in Astro says hello.
Marvelous. Well, we're all glad to have you joining us, and we hope that you will be with us.
Oh, Tariq says hi. We haven't seen Tariq for a while.
Oh, that's indeed true. Welcome back.
And then let's see here. Riley K014
Okay.
says he's out of Twitch. He says, is this actually live or just a recording?
No, this is live. We'll just call you Riley because we're friends now. But yes, Riley, this is live as you watch. And Mondays, 4 p.m. Central Time is our usual start time. And we will be going every week now as regular. We usually take a hiatus for a couple of weeks in late summer, and then we come back on. And we used to do that because in my previous job as a professor of astronomy education at the University of Arkansas, I would take breaks from the program when we had breaks in the school schedule, but I am not limited by the school schedule anymore.
Now,
I retired from my professorship last May. So,
our benefactor here, Mr. Scott Roberts.
yes, indeed.
We're getting a lot of comments all of a sudden. Pretty interesting. Cancel. He says, could LIGO be used to detect Hawking stars?
No, indeed. LIGO, at least not with current technology. The oscillations that are going on inside a Hawking star would indeed produce gravitational waves, but keep in mind that LIGO, which is a gravitational wave detector, friends, we did a program on that back in December, I believe, that is looking for events like colliding neutron stars, merging black holes, which are gargantuanly energetic. These stellar oscillations are, I would suspect, thousands of magnitudes less energetic. Possible, yes, way beyond our technology right now. That doesn't mean couldn't happen, but nothing like current technology. And we are, I think, probably at least 1,000 orders of magnitude away from enough sensitivity to detect that with a gravitational wave detector.
So, also, too, here, Misadventures in Astro asks, could you have an antimatter equivalent of a black hole?
No reason why not. No reason why not. I would think you would start identifying those because they would go ahead and be ingesting normal matter, which would be incredibly violent and bright and spectacular. And we're going to wrap it up there. If you have more questions, go ahead and you're welcome to look at our Facebook page for Explore Scientific and post questions there.
We have a Facebook page for How Do You Know?
We do. We have a Facebook page for How Do You Know? Post your questions there, and I will answer every query until the show gets to where we've got thousands a week, and then I might cry uncle. But for right now, I read and respond. You can also reach me. doc@explorescientific.com will reach me, and if you have questions, you're welcome to email me there, and I will respond.
Don't forget your book.
Indeed. So, as producer Paul reminds me to remind you, if you know someone who got a new telescope this Christmas, and many thousands of people did, maybe you were the giver, give them a copy of Star Mentor. Set their heart afire for astronomy. Keep them involved in the hobby for years to come. Thanks, everybody.
We're not responsible for house fires.
Not responsible for heart turn. This is Dr. Daniel Barth for the How Do You Know program, wishing you clear skies, and we'll see you again next week.